Howdy, this is the engineering project showcase video for the MEAN Fortress Flex team. My name is Michael Lee, and my teammates are Ian Anthony, Gavin Castro, Alexander Garrett, and Ryan Landa. For our capstone project, we worked with a sponsor by the name of Fortress, who makes industrial hazard shelters that can survive extreme situations such as a tragic gas explosion that happened in Mexico in 2012. As seen, these accidents are tragic and cause severe damage and injury to the people working there. That is where Fortress steps in to provide a shelter to retreat to if an accident like this were to occur. The Defender is the solution that Fortress came up with to deal with situations like the one in Mexico. It works great, and the company has been thriving ever since. So much so that Fortress wants to take on the residential market with a new product called Fortress Flex. It's a product that is similar in design to the Defender, but for protection against severe storms. This is where our team comes in. We were tasked with installing a power grid on the Flex to be able to power the shelter for 7 days without connection to the main grid, in case of an emergency situation to occur, such as a hurricane or tornado. This brings us to our solution-neutral problem statement. Extreme weather events compromise critical functions like HVAC, lighting, and communication in traditional storm shelters. Existing backup solutions face challenges that can't meet the project requirements. A self-sufficient power system is needed to ensure uninterrupted operation and meet safety standards during severe weather events. For the full system layout, we used 8 solar panels on top of the shelter and a generator to power the building. They are connected to an inverter that converts DC current to single-phase AC. The generator is connected to the inverter as well to enable power generation even when the sun is obscured and unable to power the solar panels. Each row of 4 panels is wired in series, and the 2 rows are wired together in parallel, enabling the lowest current we can insert into the inverter to maximize safety. For the solar panels, we chose the Tailsun 405-watt bifacial solar panel. Since we are using 8 panels, all of them in total will generate around 3,200 watts of power in order to power the kitchen appliances, as well as any other personal devices that people use inside the shelter, such as phones and laptops. The mounts we used were custom fabricated to meet the shelter's needs, resisting high winds while still attaching to the concrete structure. We chose A500 carbon steel due to its great weldability and strength. We measured and cut them at the FEDC, and then Ian welded them all together. He spent a long time working on this, and you can see that he did a great job. The batteries chosen were the DC House lithium ion phosphate batteries. We have 2 of them connected in parallel, giving us a total energy storage of 10 kilowatt hours. These were chosen due to their own battery management system that allows them to switch off when temperatures are running high to prevent battery runoff and to not injure people inside the shelter. We also used a perforated sheet of polypropylene to protect the batteries from dust and debris while still allowing for proper ventilation. After determining the specifications of the solar panel and batteries, we needed a compatible inverter that allows us to take in those voltages and currents from the panels and turn them into a single-phase AC power. The inverter that allowed us to do that is the Rich Solar Inverter, which has the specifications we need while still being the cheapest option. The generator that was chosen for the design is the Predator 12 kilowatt tri-fuel generator. As a team, we did not purchase this generator due to budget constraints, but we still designed for it. This decision was made in the spring semester. Next, we performed 2 validation tests before installing the prototype. The first was a mechanical test to measure the magnitude of deflection of the mounts under load. We designed the product to withstand up to 200 mile-per-hour winds, which we demonstrated by fastening the mounts and applying a force with an engine hoist. using a strain gauge and dial indicator, we found that the mount deflected less than 1 millimeter when subjected to a 200-pound force, which was consistent with our finite element simulations. The second was an electrical test to determine whether the solar panels met our quantitative requirements. Since half of the solar panels were used in the test, we only expected to see about half the power. We ended up with an average of 1,321 watts, which is less than expected, but because this test was conducted during the winter, where the solar radiance is lower than normal, we felt confident that our system passed this validation test. Next, I want to give a big shout out to No Label Brewing in Katy, Texas, for providing us with the space to install the Fortress Flex. We installed the solar panels on the roof of the Flex, which is 10 feet high. We began by first marking the holes with spray paint and then drilled into the concrete roof as shown here. We used a 1/2 inch bit to drill these holes, and we also used a fast drying epoxy resin for extra strength. Then we bolted the panels together in 2 rows of 4, and we used the concrete anchors to secure them to the roof. As you can see, there wasn't a lot of room on top with the panels, so it took a little bit of effort to get them all in place. Now it's time for a walkthrough of the fully installed prototype. This is the inside of the Flex, where the inverter and batteries would be mounted. Unfortunately, due to time constraints, Fortress was unable to install the drywall on the inside of the Flex, so we were unable to mount the inverter. Now exiting out the back door, we can move to the roof where we mounted the solar panels. And here we'll pass the phone to Ryan really quick. As you can see, we've installed the solar panels in 2 rows of 4. Here you can also see our custom designed and manufactured mounts, as well as the concrete anchors that we used to secure the mounts to the top of the Flex. And here's a look at the finished product. We'd like to thank the team at Fortress for the opportunity to be involved in such an awesome project. Thank you for watching.